Today, as we start our new unit on atomic physics, or technically called the nature of matter, we're going to look at some things that happen not just with the atom, but things that happen within the atom, inside the atom. We know that there are protons, neutrons, and electrons inside the atom. We know that not because we're brilliant. We know that because other people before us were brilliant, and were able to figure that out and tell us that there are protons, neutrons, electrons inside the atom. Today we're going to focus on that first particle, that first subatomic particle that was ever discovered in 1897, over 100 years ago, by J.J. Thomson. That name, if you take chemistry, will probably be familiar to you. J.J. Thomson, you learn in chemistry, devised the plum pudding model of the atom. Sometimes they call it the chocolate chip cookie dough model of the atom. The model of the atom that says, look, atoms aren't the smallest thing you can have. Rather, there is charge inside the atom. There's a sea of positive charge inside the atom. And floating around in that sea of positive charge is a bunch of little negative particles. Okay, a bunch of little chocolate chips floating around inside the dough. Okay, the chocolate chip cookie dough model of the atom, or the plum pudding model of the atom. How exactly, though, did he discover the electron in 1897? Well, he used a device that had been invented about 50 years before him. He didn't invent the apparatus. He just used the apparatus called the cathode ray tube to discover this electron. A cathode ray tube, in its most basic form, consists of, I'm going to actually draw it by hand here. Cathode ray, in its most basic form, consists of two electrodes. You got a positive end and you got a negative side. This would be positive terminal with a positive electrode. This would be the negative electrode. Now, we know now that electrons will go around, leave the negative end. They'll go from the negative end to the positive end, go through a little hole there, strike the screen down here. Prior to Thomson, we knew, or the people that were around at that time, knew that there was something leaving this terminal, this cathode, we call it. Now, I know chemistry people are going to say, wait a second, that doesn't make sense. The cathode is the positive end, right? The cathode is where electrons go to, right? Not where electrons come from. That would be the anode, shouldn't it be? We're calling it the cathode. In the end, electrons are going around here towards this cathode. Okay, we call this the cathode. I know that's a little bit confusing, especially if you take chemistry, but that's what we call it. Prior to Thomson, we knew there was something leaving this cathode. We didn't know what it was. This greenish, glowing something. Was it electromagnetic radiation, some type of light? We don't really know. Nobody really knew. Lots of theories. Nobody really knew for sure what it was that was leaving the cathode, going toward the anode, going through a little hole in the anode, and striking the screen over here. They called them cathode rays because they came from the cathode. But again, nobody really knew what they were. Thomson steps up and says, you know what? Let's introduce a magnetic field down here. So he puts a magnetic field, in this case, directed into the page. Magnetic field into the page. That caused these cathode rays, these mysterious greenish glowing, whatever the heck they are, rays, to deflect. Now these cathode rays, instead of going straight through and striking the screen, they go like this. By the way, we know they strike the screen. We know where they strike the screen because the screen is painted with this phosphorescent paint. When they're struck by these beams of the electrons, these cathode rays, the screen glows. That's the TV that's up in the corner of the room right now. There's a cathode ray inside this TV. It fires beams of electrons toward the screen of the cathode ray tube, strikes the screen. That screen is what color? Like a grayish black, right? Why is it grayish black? Glass isn't grayish black. Because it's painted. Because it's painted with a phosphorescent coating that glows when beams of electrons strike it. So when it glows, that's what you see as your picture, right? Electrons striking different pixels, okay? It causes it to glow either red, green, or blue. And then causes, if you take a real close look at it when it's on, you're going to see individual colors on that screen. Stepping back from it, they all kind of melt together to form this image that you see of your movie or of your TV program or whatever. So it's painted, which allows us to see exactly where the beam of electrons will strike. Or, at that time, these mysterious cathode rays, where they'll strike. So, he discovers that they're bent in a magnetic field. That tells Thomson one thing, not that they're electrons, not that they're subatomic particles, but it tells him that they're negatively charged particles at least. Okay, because we know that negatively charged particles are deflected in a certain direction by magnetic fields. We know the hand rule for deflection. Now, some of you are thinking, well, wait a second. How can we know that negative particles are deflected in a certain direction by a magnetic field when we didn't have any concept of electrons? How can we know about charge when we didn't know about electrons? Electrons didn't exist, at least in our minds, before 1897. So how is it exactly that we know that negative particles would be deflected in a certain direction in a magnetic field? Listen, we knew about charge for a long time prior to Thomson. We just didn't know where the charge came from. We didn't know that it was electrons and protons that made up negative and positive charge. We just knew about charge. Okay, think about it. In 1819, Ørsted discovered that moving charges generate magnetic fields. So in 1819, we knew about charges. We just didn't know what those moving charges were. We just didn't know that they were subatomic particles. So it was well established that negative charges would deflect in a certain direction by a magnetic field. So this section of the cathode ray tube here tells Thomson that we have negative charges. Not that they're subatomic, not that they're electron, but that the charges, that they're negative charges. They're not beams of electromagnetic radiation. They're not beams of light. Okay, they're beams of negatively charged particles that are leaving this cathode, going towards the anode, skipping through the little hole in the anode, and then striking the screen. Thomson's a smart guy. He says, well, wait a second. I know how to deal with this. I know how to deal with it when charged particles get deflected in magnetic fields. Lots of people have done that. I know that they move in a circle, so they experience a centripetal force, and we know that centripetal force is equal to the magnetic force that's causing it. In other words, mv squared over r equals qvb. This isn't even new for you guys, right? It wasn't new for Thomson, isn't new for you guys either. Did this back in our magnetism unit. Cancel the v's here. So we got mv over r equals q times b. Says, well, look, I want to know what these particles are. So let's try to calculate some property of these particles. He measures the value of r, the radius of the path, based on where it strikes the screen. That's actually a relatively easy thing to find, just based on where it strikes the screen. He measures the value of B. That's easy because he introduced the magnetic field. He controls how much magnetic field is there. So he knows the value of B. But he doesn't know what the value of M is. What's the mass of these particles? No idea. What's the speed of these particles? No idea. What's the charge of these particles? No idea. Well, he wasn't very successful here at this point because I think you got an equation with 5 variables. You know 2 of them. You don't know 3 of them. That's not much to go on. But remember, he's a smart guy. So he introduces another section of this cathode ray tube. In the middle, in between where these particles accelerate and where these particles are going in a circle. This section also has a magnetic field. But this section will also have an electric field caused by a couple plates. That causes, if we do the hand rule for deflection, thumb, fingers, palm, a magnetic force downwards, but it causes an electric force upwards. Now, for lots of these particles, they're all going at different speeds. For lots of these particles, the magnetic force might be bigger than the electric force. And those particles would deflect downward and never even make it to this red chamber right here. For some of the particles that are going the wrong speed, the electric force might be bigger and they deflect upwards and they never make it to this red chamber here. But for particles that are going just the right speed, the magnetic force will balance the electric force. What happens to those particles? If those two forces are balanced, the force upward balances the force downward, what happens to those particles? They cancel out, yeah. So in other words, the particles are just going to keep going straight through, right? They enter this third chamber, this red chamber right here, where we can do this analysis Fc equals Fm. So let's analyze this. For the particles going straight through, undeflected, Fe would equal Fm. Now, that's not the case for all the other particles. But the other particles we don't care about because they never make it into this red chamber. We care about the ones that go straight through, that make it to that third red chamber. And for those particles, Fe must equal Fm. The electric force acting up must equal the magnetic force acting down. Q's cancel. The speed of these particles ends up being equal to the electric field strength divided by the magnetic field strength. Now, Thomson introduced both of those. So he knows the value of B. He knows the value of E. Well, look what he can do. He can calculate the value of the speed, not for all the particles that are leaving the cathode, but for the particles that are going just the right speed to go straight through that middle black chamber and then enter that third red chamber. So now he's got the speed. Which you can plug into here, because the particles that make it to that third red chamber must be going that speed. So now what does he get? Well, let's change this to a green one now because we know the speed. Now he's still got two unknowns, but the balance has shifted. He still doesn't know mass, he still doesn't know charge, but he knows more than half the variables in there at least now. All right, got a little analogy for you, and I've used this analogy for a lot of different things, but we'll use it again. Okay, Simon, you're 17 years old, right? Okay, I'm 34 years old. Somebody comes into the classroom, some stranger comes into the classroom for reasons that I'm not aware of. Normally, we don't have strangers coming into the classroom or in the school. But let's pretend we do for a second. And he comes up to Simon and says, hey, how old are you? Simon says, I'm not telling. Why not? Well, my parents always told me not to talk to strangers. So Simon's not telling him how old he is. Then he asks me, how old are you? I say, I'm not telling. He says, well, why not? Well, you don't ask an adult how old they are because it's kind of rude. So the guy's like, well, I don't know how old he is. I don't know how old you are. And then I say, well, you know what? I'll tell you what. I'm twice as old as Simon. I'll tell you that. So the guy walks away, doesn't know how old Simon is, doesn't know how old I am, but he at least knows the ratio of my age to your age. Right, Simon? He wanted to know your age. He wanted to know my age. He doesn't know either one, but at least he knows something. He knows more than he came in with. He feels like he's accomplished something, right? He knows the ratio of our ages. Thomson couldn't find charge. He couldn't find mass. But he said, look, if I can find the ratio of the charge to the mass, that's better than nothing. That's better than what I had before. So he takes that, take the m down by dividing. Becomes Q over m. Then take the b down by dividing. Q over m is equal to v over br. Now, don't quote me on this, but I think the value that he got when he did the math there, I believe, well, I should have checked this before class, but I believe it's 1.76 times 10 to the 11 newtons per kilogram. It's a big number. If the ratio of charge to mass is so big, what does that tell you about the number on the bottom? What does it tell you about the value of the mass? We don't know exactly what it is, but we do know that it's really small. This number was so big, this number, this ratio of charge to mass, was bigger than any other charge to mass ratio ever measured. Because it was so big, the mass had to be so small that the particle had to be smaller than any other particle ever discovered. In other words, it had to be smaller than the atom. So now we have not just negative charges moving through this electric field and magnetic field and then finally through this red magnetic field. They're negatively charges that are smaller than atoms. In other words, they're negatively charged subatomic particles. That's the first discovery of anything smaller than the atom. And it all comes because the charge to mass ratio is way too big to be any atom that we've ever discovered. The mass is way too small to be the mass of an atom. It's got to be something smaller than an atom. So it's got to be inside the atom or subatomic. Does that make a little bit of sense? So this is essentially what I just said, right? Thomson measured the charge to mass ratio of the electron, which was Q over M. He didn't know charge, didn't know mass. Okay, 34 divided by 17 is 2. I'm twice as old as Simon. We got the age-to-age ratio by dividing my age by Simon's age. We didn't get the charge to mass ratio by dividing charge by mass because we didn't know what charge and mass were. Rather, we got the charge to mass ratio by dividing V by B times R. But it gives us the same thing. Still gives us the ratio of Q to M. And again, it's so big, the mass had to be so small, right? This number, really, really big. The number on the bottom, really, really small. But they had to be subatomic particles. We already knew they were negative because of the way they deflected in the magnetic field. Now we've got the discovery of electrons. Now, his model of the atom that came from this, we alluded to this a few minutes ago, right? The plum pudding model of the atom. It was all wrong. Well, almost all wrong. Like, that's not even close to the model of the atom that we have now. Electrons circling around the nucleus with protons and neutrons in the nucleus. Not even close. Not even close. But it was the first time that we had the acknowledgement of something smaller than the atom. Something accurate. The electrons smaller than the atom. He just didn't know what was happening inside the atom with these electrons, just that they were there somewhere. So he said they're floating around in the sea of positive charge, but didn't really know. Didn't really know for a little while after Thomson, till a guy named Rutherford. If you've taken chemistry, remember Rutherford. You guys remember Rutherford gold foil experiment? Planetary model of the atom? We'll talk about him in a couple days as well. All right, make some sense? All right, so when you take a look at this, there's two sections of this cathode ray tube right now that we know how to analyze. Right? We can analyze sometimes what I call the main chamber here, the red chamber. Then you got the black chamber, or sometimes I call that the velocity selection chamber, because you're selecting a velocity to go through. The rest of them either go up or down. Well, there's also this first chamber over here that we didn't really pay much attention to, where charged particles accelerate from the cathode to the anode. These cathode rays, these mysterious cathode rays that we've shown to be electrons, accelerate. Well, when charged particles accelerate, we use conservation of energy, EI equals EF. So here, you could use QVI equals 1/2 mvf squared. Now, some of you might say, well, why wouldn't I just solve for V this way? That's easier. Well, solving for V there gives you actually the maximum possible speed, not the actual speed, because that assumes that the energy conversion is 100% efficient. And in reality, it probably isn't. Most of the particles probably aren't going this fast. They're all going different speeds. This is just the fastest possible speed. We don't want the fastest possible speed as we go into this third chamber here, this red chamber. We want the actual speed. So what we do is filter out a bunch of different speeds, keep one speed left, this speed right here, to enter this third chamber. But there are three chambers that you might have to deal with in a problem. There's what we call the acceleration chamber right here. There's the velocity selection chamber right here. And then there's what I call the main chamber right here. Every time you get a question involving the cathode ray tube, you got to first identify that it's a cathode ray tube problem, but then you got to identify which chamber it is. It's kind of two parts to each question. All right. Let's look at our first example on page 576, chapter 15 here. It says a beam of electrons passes undeflected through a 0.5 Tesla magnetic field combined with a 50 kilonewton per coulomb electric field. Don't like that, kilonewton, right? Newton per coulomb is fine. Kilonewton per coulomb, not so much. The electric field, the magnetic field, and the velocity of the electrons are all perpendicular to each other. How fast are the electrons traveling here? We got a magnetic field here. We got an electric field here. This is a cathode ray tube problem. These beams of electrons are going in a cathode ray tube. Can anybody tell me which section of the cathode ray tube it is, though? The acceleration chamber, or the velocity selection chamber, or the main chamber? Look at your pictures. Look at your picture on your page. Look at what we have given to us here. Tell me which section of the cathode ray tube this is. And you'll look like you're ready to give me an answer there. Do you think you have one? It's the second part. Good. How do you know that? Good. Okay, perfect answer. That's where you have an electric field and a magnetic field. In the first section, you don't have both of those. In the third section, you just have a magnetic field. The second section is the only section where you have both electric and magnetic field. Now, there's one more word there that would lead us to the same conclusion that Daniel just drew, just in a slightly different way. Let me spot that one word. I'll give you a hint. It's in the first sentence. Undeflected. Undeflected. Okay, it's the velocity selection chamber where these particles go undeflected. All right, so we're dealing with the velocity selection chamber. In the velocity selection chamber, we say Fe equals Fm. The upward electric force equals the downward magnetic force. QE equals QVB. I'm deriving this again because it doesn't appear on our data sheet, and we need to be able to do this for our test. Now, if you can remember it, all right. But as far as I'm concerned, I've told you this before, let's not memorize anything that we don't need to memorize. Let's figure it out each time. V equals E over B. The electric field is 50 kilonewtons per coulomb, 50,000 newtons per coulomb, and the magnetic field here is going to be 0.50 Tesla. 5 times 10 to the 4 divided by 5 times 10 to the negative 1 gives me, I believe, 1.0 times 10 to the 5. Is that right? So some of the electrons in this cathode ray tube may be going faster than that. Some of them may be going slower than that. But the ones that are going faster or slower will be deflected upwards or downwards in the velocity selection chamber, and then they'll never make it to that third main chamber where we do the main part of the analysis for charge to mass ratio. These ones are going undeflected. These ones are the ones that are entering that third chamber, the main chamber. So these ones are the ones we care about. Is that a question? Yeah. How? So EI equals EF. So QVI is equal to 1 FMV squared. Okay, so Simon's asking a really good question here. Couldn't you find the mass in this first section by using QVI is equal to 1 FMV squared? Well, if you plug everything else in and solve for mass, yeah, you could. But there's an issue with that. In fact, there's two of them. One, if we solve for the speed in the second chamber here, which we can do, remember that's the speed of some of the particles, just the ones that are going straight through. It's not the maximum speed, and that's what this speed is right here, is the maximum possible speed. So it's not necessarily the same speed. Could be, but not necessarily the same speed. The other issue is, Simon, we don't know what Q is there. So just the same as in section 3 when Thomson found the charge to mass ratio, didn't know what Q or M was, didn't know what Q or M is here either. Okay. Now, if you're really good math-wise, you might say, well, if we have the speed, we could set up some kind of substitution or elimination to find two equations, two unknowns, right? Q and M in both of them. But again, this speed, the connection there is kind of dubious. Okay? It's not necessarily the same speed. Okay? Good idea, though. It's a really good idea. Okay, does that one make sense? That's not too bad, eh? You're going to get some problems here. 3 of them. I want you to identify, first of all, for all 3 of them, what chamber it is. And then go from there. I'll give you a few minutes to work on those. All right, if we're not having any issue with those questions, let's take a look at 15.2 on 758, sorry. Have a quick read there. Just have a quick read at it, and then tell me if there's anything that jumps out at you, anything that you don't recognize, anything that's kind of puzzling, anything that leads you to a strategy, any words that come to mind. Tom? Okay, both circular and perpendicular. What does that tell you, Tom? Sorry. Okay, fair enough. Fair enough. I just stood out. That's the question I asked, right? Is there anything that stands out to you? So, yeah, that's the question. Good. Anybody else add to that? If the charge is going in a circular path, perpendicular to the magnetic field, which section of the cathode ray tube could this be? Third section, right? Now, in the end, you could have solved this problem 2 units ago. You didn't need to know anything about the cathode ray tube in order to solve this problem. When a charged particle is going in a magnetic field, it goes in a circle. And when it goes in a circle, we say FC equals FM. Just 2 units ago, the concept of charge to mass ratio would have been a completely foreign concept. Okay, now you know what that is. Now you know what that means. 2 units ago, you would have had no idea what that meant. But you still could have said FC equals FM, and therefore, mv squared over r equals qvb. Cancel with the v's. mv over r equals q times b. We want to solve for not q, not m, but q over m. So we're going to take the m down by dividing. It becomes q over m. And then we're going to take the b down by dividing. So it becomes v over b times r. Well, if we know q and we know m, that's the easiest way to find the charge to mass ratio. But look, if you know q and you know m, there's no reason to even do a cathode ray tube experiment if you know q and m already. The only reason we do it is to get v and b and r to indirectly find q over m. Simon, question? Okay, fair enough. I did it all at once. I shouldn't have did it in one step there. Okay, let's do it in steps here. Okay. So we get mv over r equals q times b. We want q on the top, right? We want m on the bottom. So let's take the m down by dividing. It becomes v over r equals q over m times b. Does that make sense? Okay, now we want to get b on the bottom. So we're going to take it over to the other side by dividing. So it becomes v over b times r equals q over m. Okay? And then I just wrote it the other way around. I just wrote it q over m equals v over br. Does that make sense to everybody? Okay, that's a good question. Why do we want to be able to rearrange, take that form, as opposed to just memorize it? Because look, you got so much stuff to remember. If you try to memorize this equation, which doesn't appear on your data sheet, there's a pretty good chance you're going to make a mistake with it. Be able to figure it out. And if you're not sure how he did it, then ask the question. All right, we don't know Q, we don't know M, so we're going to have to find the charge to mass ratio indirectly. V is 5.93 times 10 to the 5 meters per second. B is 100 microtesla, so it's going to be 100 times 10 to the minus 6 Tesla. Ladies? And R is going to be 3.37 centimeters, which we're going to put into meters, 0.0337 meters. I should have, when I first saw this question, circled these, right? To remind me to do the conversions. Now, I remembered to do the conversions here. Sometimes you will too if you don't draw attention to it. But you're more likely to remember to do the conversion if you do draw attention to it. Let's do the math here. We'll do this together, just to make sure that you guys can use your calculators properly here. We got 5.93 times 10 to the 5. Let's divide that by, use some brackets here on the bottom, 100 times 10 to the minus 6 times 0.037, 0.337, I should say. Now end that bracket. What did I get for a value here? 1.76 times 10 to the 11 coulombs per kilogram. I think that's what I told you it was, right? When I introduced this. Said we found the charge to mass ratio, found it was so big. I think I told you it was 1.76 times 10 to the 11. I just couldn't remember for sure if I had the right number there. My 34-year-old brain is still kind of working at least. All right, let's take a look at those three questions, please, that go along with that example.